In this video, we are going to talk about exponential and logarithmic functions of complex numbers. What you know from real numbers, exponents, and logarithms will help you immensely because it is very similar. However, there are some differences, so it's important to know those differences. And as you may have guessed from the time we have taken to learn how to write complex numbers in exponential form, these topics will be important throughout this course, so it's important to get to know them well. We will start with a complex number in exponential form, e to the z, which can be written as e to the x plus I y, and then using the property of the product of two exponents, we can convert this to e to the x, e to the iy, and then we can convert using Euler's identity, the e to the iy, to cosine of y plus I sine of y. Other expected properties is the product of two exponents is equal to the exponent to the sum of our two exponents. Similarly, if we have an exponent divided by another exponent, we can have the exponent simplified to e to the the numerator exponent minus the denominator exponent. Something a little different, but very similar to positive exponents, e to the 1n is the nth root, but for real numbers you can have positive and negative numbers. For a complex, we're going to define e to the 1n as the positive nth root. The derivative is the same as for real numbers, so the derivative of e to the z is equal to e to the z. And then also, like real numbers, e to the z never equals 0. Not as expected, so properties that are different is e to the z is periodic with an imaginary period of e to the 2 pi I, and we'll see why that's the case. We'll look into that. And e to the z also can be negative, unlike real numbers. E to the I pi, for example, is equal to -1. We will then go and look into logarithmic functions and to determine, and this is of complex numbers, so it's different than real numbers. To determine how we're going to define the logarithmic functions, we're going to look at solving the problems of the form e to the w equals z. We will use this kind of steps, this algorithm here, to develop a formula which is going to be, in this case, w is equal to natural log of r plus I theta plus I 2 pi n. So this is a multi-valued function, which is important to realize that this has multiple solutions, unlike in real numbers. But once we have this, we're going to use this motivating problem to define the logarithmic function of a complex number. And here we have the definition that log of z, and now we write z as an exponential, log of r e to the I theta is equal to the natural log of r plus I theta plus I 2 pi n. And one thing that I thought was strange when I first looked at this is the fact we said, oh, we're going to figure out how to define the logarithm, and then we have this natural log here. And so it's like, so what are we doing with if the whole big deal was finding what what logarithm is, why do we have a logarithm here? And the answer is because this is natural log of r, and r is a real number. So this is the real number. This is the logarithm of a complex number. As we had mentioned, it's a multi-valued function, so we do have a principal value, which would designate with a capital L. So if you start a sentence with lowercase log of z, and it's this multi-valued, you should keep this lowercase, even though it's the first word of a sentence. That's what I would do anyway. So log of z, capital L, is where we have n equal to 0, and this is our principal logarithm. Then we have another note here that we will talk about, and then we have some examples as well as other examples in this video. Many of these expected properties, and this first one we've already been using, but we'll just go over this top one here, the exponential form of a complex number. If I take the z and rewrite it as x plus iy, and then this is equal to e to the x, e to the iy by this property here, I can rewrite then e to the iy as cosine y plus I sine of y. And this is using Euler's identity, which is e to the I theta is equal to cosine theta plus I sine theta. The other properties here, the product of two exponents, you can just add the exponents and you have this equality. Or if you have the division of two exponents, you can subtract the denominator from the numerator. We also have the property e to the 1n is the positive nth root, whereas in real numbers you might have a positive and negative root. Here, for complex numbers, we only consider the positive nth root. The derivative of e to the complex number is just e to the z, just like for real numbers. And then also for like real numbers, e to the z is never equal to 0. I am not going to prove any of these. We're just going to take them and use them. For these properties here, properties that are not as expected, I will show that e to the z is periodic. To show it is periodic, I am going to show that e to the z plus 2 pi I is equal to e to the z. And so here, this is the definition of periodic. At some later time, these two functions have the same value. For whatever value of z, you're separated by 2 pi I. And this is a pretty easy calculation. So e to the z plus 2 pi I is equal to e to the z times e to the 2 pi I. And now because we know e to the 2 pi I equals 1, that is equal to e to the z. So this is kind of summarized up here. And just to review how we find that e to the 2 pi I equals 1, and then we'll also do e to the pi I is equal to negative 1. And we may have emphasized this already. I know it's been introduced already, but because some of these videos are done out of order, I'm not sure how much it's been emphasized, so I'll just review this. Here we have an r, a radius of 1. So we're out here at radius 1. And then to find the angle between the positive x-axis, we go around 2 pi. So from here, and in the counterclockwise direction. So when we come all the way around at 2 pi, we're back at 1. And just looking at e to the pi I, so in that case, our angle between the positive x-axis and our number e to the 2 pi is just pi. So we're just going to come around pi radians, and we get to -1. Next, we will move on to logarithmic functions of complex numbers. To develop a formula for logarithmic functions of complex numbers, we're going to use the motivating example of solving the problems e to the w equals z. And I'll clear some of this out to give us more room. I have moved our motivating example over here, and I wanted to note if w is real, we could simply take the log of both sides, and then we would get w is equal to log of z. So again, this is only if w is real. We will find when w is complex, our solution is going to be natural log of r for once we have w in exponential form, that is w is equal to e to the, r e to the I theta, then our solution is going to be w is equal to natural log r plus I theta plus I 2 pi n. I moved my problem over here, and I'm going to work it in this column. I'll do an example at the same time in this column here, and over here I'll just write what step we're working on. So my first step is here, put the right-hand side in exponential form. So I moved the step here, so you can see the right-hand side of the equations. Over here I have my complex number, which I'm going to write as r e to the I theta. That's my exponential form of a complex number. For my example, where my complex number is 1 plus I, first I'm going to identify my x is equal to 1 and my y is equal to 1. So my r, my radius in exponential form, is going to be x squared plus y squared. That would be 1 plus 1 squared, which is square root of 2. Now I need my theta over here. So 1 plus I in the complex plane, I'm going to go over 1 for x and 1 for y. Remember, this is my x for the imaginary part. So I have this point here, this vector, which means my angle now here between the positive x-axis and my vector is going to be pi over 4. So here I have my 1 plus I in exponential form is going to be square root of 2 e to the I pi over 4. My second step here is to put the left-hand side of the equation in the form of x and iy. So this part here, my w, which is going to be equal to w1 plus I w2. I don't want to put x's and y's since generally that's going to be this side of the equation, although I really could have because here we put this in form of r and thetas. But so my x is like w1, my y is w2. So this is going to be e to the w1 plus I w2, and then by our properties, this is equal to e to the w, e to the I w2. And then I just brought my right-hand side down. Okay, so that's for the second step. For my example here, my z, I'm going to just make it equal to x plus iy. So we have e to the x, e to the iy, and I bring down the right-hand side is square root of 2 e to the I pi over 4. Finally, my last step is to equate the right hand to the left-hand side and solve for x and y. So these two are equal. When I look at, well, I've already equated them, but looking at this, this is an e to the I omega 2, or w2, which is in this form here. So my e to the I w2 is equal to e to the I theta. This here, this e to the w, remember w1 here is a real number because this is my x and this is my y. So this is a real number. So this is like the radius r. So e to the w1 will equal to r, and e to the I w2 will equal to the e to the I theta portion, which means that w1, now here I can take the natural log of both sides because w1 is a real number, r is a real number. Taking the natural log, I have w1 is equal to the natural log of r. Over here, what this tells me is w2 is equal to theta. This is actually my x and y. So coming back to my then example, if I have these two equated, again, x is a real number, and here I have e to the iy. So this e to the iy, I'm going to match up with the e to the I pi over 4. And here, my real number, I'm going to match with my square root of 2. Which means that x, taking the natural log of both sides, and I can do this natural log. Like I know right now, I'm trying to find a formula for the logarithm of complex numbers, but this is the natural log of a real number, and I know how to do that. So here I take natural log of both sides, and I get x is equal to natural log of 2. Natural log of square root of 2, sorry. And over here, this tells me that y is equal to pi over 4. So my final solution for z is again equal to then my real part plus I times my omega. And then also I have to remember that when I did my omega, I could actually come back around 2 pi and I get the same solution. So I need to add 2 pi n. Same thing over here. I have my x coordinate plus my I and my y, but to my y I can actually add 2 pi n and still have the same vector z, or same complex number. So here is my solution, and this is the solution to my example. I also want to mention the way we took this e to the x plus iy, and now I'm just saying it in terms of x and y, but I guess I should say e to the real part plus I, the imaginary part. The way we broke that down and then said e to the x, or e to the w1 was equal to r, and e to the I w2, or our y, would set our y equal to theta. We are going to use this type of trick in a couple of slides later. So keep this kind of trick over here that we used in mind. Coming back to my overview slide just to see where everything is, this is the same example I had, e to the z equals 1 plus I. I have the steps written down, plus I have what I did for the example. And then in general, this was the general form which we had derived in the previous slide. Z is equal to natural log of r plus I theta plus I 2 pi n. So again, this just came directly from the previous slide. And the significance of the I 2 pi n is that this logarithmic function for complex numbers is multi-valued. In other words, there's not just one value that gives you the solution. The solution is multiple values. And this will become significant both in the next video and also later when we're doing integrals. So this is something that's important for you to remember and see how to work with that, because it will come up again. And looking at how this kind of example is going to help us define the logarithmic function of a complex number. Remember, we wanted e to the log w equal to z. Actually, it was like log of e w equals z, sort of the opposite, the log and the e. But anyway, it's really, they're inverses is the idea. So if you want this to equal to z, then that must mean here, this log of z must equal to the natural log of r plus I theta plus 2 pi n. So this came exactly from our motivating example. So using the motivating problem above to define logarithm of a complex number, consider if we want e log of w equal to z, then log z, if we take the log of both sides, must be equal to natural log of r plus I theta plus 2 pi n. Next, we're going to look at this result. I'm going to clear some of this stuff out, look at this result a little bit closer. We are going to go back to our motivating example and see how it connects to our logarithmic formula here. We sort of derived it with our motivating example, but we want to make a few more points. So from our motivating example, we had e to the w equals z. And if it were a real number, we kind of want to be able to take the log of both sides. For a real number, this would just be w is equal to log of z. So this is how we would define log of z. So let's look at that again. So if w is real, in other words, x, if this is a real number now, here, if w is equal to x plus I0, then e to the w is equal to e to the x plus I0, which is just e to the x. Also, looking at w is in exponential form, which is equal to r e to the I theta. If we compare that to e to the x e to the I y, as we did in the previous work, we said then that r must be equal to e to the x. That's the real component. And then this will give us y is equal to theta. And since y is equal to 0 because w is real, that means this goes to 1. So what we have is r is equal to e to the x. And we also have from over here that e to the w is equal to e to the x. So e to the w here is equal to e to the x, which is equal to r. So now we can take the log of both sides, and we get log of e to the w is equal to natural log of r. And so we get w is equal to natural log of r. And this, again, all depends on our w being real. And looking how that fits in with our formula, which I brought down here, so now we have log of z is equal to natural log of r plus, and in this case, we've already determined that y is equal to 0. So for this, we have that we're going to define log of z equal to natural log of r, which is exactly what we have here, right? We wanted log of z, which is equal to e to the w, is equal to natural log of r, which is intuitively what we want. Because if w is real, again, the real part will give us w is equal to r, and then this here would be equal to 1. So the natural log of z then should give us natural log of r. I want to contrast that if w is complex. And we're not going to do the same sort of calculation we just did for real, because that's exactly what we did when we did our motivating example and we followed the 3 steps. So I'll let you go back and look at that again if you want to contrast the steps with how we did it for the complex numbers. But I do want to say, first, that if w is complex, our motivating example, we can't just say log of e to the w is equal to w. That is not true. Which you sort of get from the formula here, because otherwise it would stop at natural log of r. So there is this extra stuff, and I just wanted to talk a little more about that extra stuff. So looking at that log e to the z, and now instead of having e to the w, I just renamed w to be z, because this z here is no longer going to play into our conversation, so there shouldn't be a confusion. If I had named this z, that would have been confusing. But now e to the w is just e to the z to highlight the fact that this z is complex now. Our solution told us it's natural log of r plus I theta, and actually I'm just going to use the principal. So I have natural log of r plus I theta, where theta is our arg z. In other words, it's bound between negative pi and pi. So if I look at the modulus of z, you kind of already know that this is going to be equal to r, because this is the length of e to the z from the real axis. But we will break it down. So this is going to be e to the x plus iy, which then we can write as e to the x, e to the iy, and comparing that to exponential form, which is r e to the I theta, we say that e to the x is r, and over here we have y is equal to theta, and we've used this a couple of times already. So this here, this modulus, we're expecting this modulus to be equal to e to the x. That's the radius. And then also our arg e to the z, now our angle between here is going to be equal to y. And oh, I'm sorry, this is lowercase arg z, so we need to add the 2 pi n. So I got rid of that restriction here because actually this was lowercase a, not capital A. Capital A would have been restricted between negative pi and pi, but now we're not restricted because this is lowercase arg. So now looking at this formula, my log of e to the z, in this case r is equal to e to the x plus I, and my theta I'm going to replace with y plus 2n pi. So now natural log of e to the x is just equal to x, and then here I have my plus iy, and then I also have this extra stuff, my I 2 pi n. So this is equal to z plus the extra stuff. So that's where this extra stuff comes from. And again, when w is complex, you can't just take the logarithm and get w. We have a multi-valued function here. And this is exactly the difference. This extra stuff is the difference between complex and real logarithms. Our last discussion is noted here. So log of e to the z is not just equal to z, but it's equal to z plus I 2 pi n. And I kind of outlined that argument here that we had on our previous page. And the principal value of log z is the value obtained when n is equal to 0. I have this quick example. Log of 1 is equal to log of e to the 0, which is equal to natural log of 1 plus I0, which is equal to 0. To review what we have covered, both about the exponential and logarithmic functions, we started with e to the z, z being a complex number, is equal to e to the x plus iy, which is equal to e to the x, e to the iy, and using Euler's formula, we can substitute for e to the iy cosine y plus I sine of y. We had some expected properties, such as when we multiply two exponents, we can just add their exponents. Also, similarly, when we divide two exponents, we can just subtract the denominator from the numerator. We also looked at e to the 1 over n and pointed out that for a complex number, this is the positive root, nth root. If we were doing real numbers, we could have positive and negative roots, but for complex, we only look at the positive nth root. The derivative of e to the z is equal to e to the z, which is nice, and also e to the z never equals 0. Some properties that are not as expected is 1, e to the z is periodic with the imaginary period of I 2 pi. We derived this and the outline of the derivation is here. We also noted that e to the z can be negative, and our example was e to the I pi is equal to negative 1. Next, we wanted to look at logarithmic functions of complex numbers, which does differ from logarithms of real numbers. And we started with this motivating example. We wanted to solve the equation e to the w is equal to z. And if this were real numbers, we could just take the log of both sides and we would get w is equal to log of z. But what we will find is when we do this for complex numbers, our solution for w is equal to natural log of r plus I theta plus I 2 pi n. And I'm also going to point out in our review, when we take the log of e to the z, which will give us, it doesn't just simply give us z, it gives us z plus this extra stuff, and we did discuss that. But here when we were solving our motivating problem, we did this using 3 steps. First, and we also had an example, so I'm just going to review the example here. If our example is e to the z is equal to, and this complex number is 1 plus I, the first thing is we put the right-hand side in exponential form. So the right-hand side of the equation is 1 plus I. We put it in exponential form, r is equal to square root of 2, and 1 plus I, the angle is pi over 4. The second step was to put the left-hand side in the form e to the x, e to the iy. So this is our left-hand side of this. So we have this is our right-hand side here is equal to e to the x, e to the iy, and now we can equate the left-hand side to the right-hand side. So what we note is that this here is the real part, square root of 2, and e to the x, since x is a real number, this is the real part. So we equated these two together, and then we have e to the I theta is equal to e to the iy, which gives us y is equal to pi over 4. So that meant our solution is equal to z, and then, first we solved for x, which taking the natural log of both sides. And now we can do this because x is a real number. So we can take the natural log of both sides and get what we were expecting, which is x is equal to 1/2 natural log of 2. So now z is equal to 1/2 natural log of 2 plus I, and then our y is pi over 4. And what we came to see is that, or one of the things we noticed is that our angle didn't just have to be pi over 4, it could be pi over 4 plus any n times 2 pi. So we needed to add this on, I to n pi. So this was how we solved this particular example, and the general form which we also solved would give us natural log of r plus I theta plus I 2 pi n. And again, this is a multi-valued function, and that's the big difference between real and complex logarithms. Here we can have multiple values because of the periodicity. So we have then the logarithmic function of a complex number taking this equation here is equal to, and by the way, z is equal to r e to the I theta. Once we put it into this exponential form, we can just read it off as natural log of r plus I theta plus I 2 pi n. And then if we want the principal value, we denote that with a capital L. Log is equal to natural log of r plus I theta. That is, n is equal to 0. And then last, we have this note that log e to the z is not simply equal to z, but z plus I 2 pi n. And we derived this, and we also, you can just then compare this to our solution here. It's more clear in the derivation. And we did one last example, which was log of 1 is equal to log of e to the 0, which is equal to, according to our formula, natural log of 1 plus I and then 0, which is just simply equal to 0. Last, I have 4 problems for you to try. The first one is e to the z equals -1 minus square root of 3i, and you're asked to solve for z. The next is to evaluate log of -1. The third problem is to show that e raised to the 2 plus 3 pi I is equal to -e squared. And last, if e to the z is real, then show that the imaginary part of z is equal to n pi. Here are the solutions to the 2 problems. I will go over this calculation of theta. It's the second time we've had a problem like this, and I'm always initially thrown off or I forget something. So on the next slide, I will say something about that. But I'll give you a minute to look, actually not a minute, I'll give you seconds to pause the video and look at the solutions first. When putting this complex number into exponential form, we need to calculate theta, and I often use the formula inverse tangent of y over x. And the thing you need to remember is if this is negative and this is negative, you're in the third quadrant, right? Because we're at -1 on the x-axis and -1 on the y-axis. So you're in this third quadrant. So when you use this formula, you're actually measuring this angle here because you're using this coordinate of, in this case, negative square root of 3 and this coordinate of -1. But when you want to calculate theta, you need to calculate it from this positive x-axis. So once you figure out the inverse of -3 over -1, which is equal to pi over 3, so it's in the third quadrant, but to get the measurement from the x-axis, you need to add pi. You need to add this many radians. So I'm going to add pi to my pi over 3, and I get 4/3 pi. But now, remember, we want our theta to be between negative pi and pi, and 4/3 pi is too big, so I need to subtract off 2 pi. So I'm going to go from here, I'm just going to go all the way around again, and what I get is -2/3 pi. So this is how I got my theta. And here are the solutions for the last 2 problems. And that's it for this video. Thank you for watching.